Hello everyone. In this video, we are going to perform some calculations to better understand the nuclear power plant's operations and maintenance. Here we have an example of a nuclear power plant with the gross reactor power of 1160 megawatt electric. It assumed to have two turbines providing 580 megawatt electric per turbine. For simplicity, we are going to name these turbines Turbine A and B. We have a net power of 1100 megawatt electric, and the reference period is 1 year, which means all of our calculations will take into account a year of operation. There are plant outages of 3 weeks for maintenance and refueling. And lastly, we have operating conditions, which will have an impact on the load power of the power plant. There are conditions like high temperature, environmental condition, and one of the turbines will trip for some time, and grid frequency regulation, which means the grid will reduce the demand. Therefore, we will have to adjust our power plant for this change. Let's start by writing the most important data. So we have reference period time of 1 year. We are going to convert this to hours. So later on, we can calculate the unit of megawatt hours. So 1 year in hours, 8,760. Then we have the plant outages for maintenance and refueling. And here we know that it will take 3 weeks. So converting to hours, 7 days, 24 hours, 504 hours. And we are going to calculate our reference energy generation. And this parameter just shows us if we assumed a year of operation and the plant continuously works non-stop within this period of time, how much energy it would generate. So reference energy generation. Abbreviation is REG. And how is it calculated? It's calculated by the reference period time in hours times the net power of the power plant in megawatts. Gives us the reference energy generation. So let's plug in the numbers. We have the reference period time in hours, 8,760 times the net power of 1,100 megawatts. As you can see here, which gives us 9,630,000 megawatt hour. All right, so now we can calculate our energy losses. And when we calculate the energy losses, we are going to separate them into 3 categories. The first one will be the plant losses, which means our maintenance and refueling time. We know that for 504 hours, the plant will be shut down for the maintenance and refueling, and this is a plant loss. This is something we expected. Times the net power of the power plant, 554,400 megawatt hour. Okay, so this is the only plant loss that we have. And what are the unplanned losses? UEL. If you recall, in our question example, we know that one of the turbines tripped for 1 week here, as you can see. So this is an unplanned loss. We didn't really plan ahead. One of the turbines would be out of commission. So we will include this loss, obviously. And let's write here, turbine B trips for 1 week. We are going to convert 1 week to hours. We get 180 hours. And then we are going to calculate how much we lost. So 168 hours times 550 megawatts. And why 550? Because each of the turbines provide 550 net power. So one of them is out of commission, but turbine A still works. So we get 92,400 megawatt hour. All right. So the third category of the losses is the external losses. And what does it mean, external losses? I think it's XEL. Yes. So here, if we go back to our example, we know that there was a high temperature. This is an external factor to the nuclear power plant. And also the demand was reduced. And these two impacted our power plant load. So let's calculate it. We know the high temperature happened for 6 weeks and the load was reduced to 92%. And the grid frequency caused the load to reduce to 97% for 12 weeks. Let's start our calculation. Let me pick another color. So first, the high temperature, let's say weather, and 8% loss, because we saw that the load reduced to 92%. 100 minus 8, 92. If we quickly calculate this loss, we have normally 1,100 megawatts power when the MPP operates at 100% power times 0.08, which is for this 8% loss, we get 88 megawatts loss. So this happened for 6 weeks. So during this 6 weeks period, let's calculate how much energy we actually lost. So 6 weeks in hours, 1008. Then let's calculate 1008 hours times 88 megawatts, which gives us 88,704 megawatt hour. And the second external loss we have is the demand. Demand was reduced about 3%. So our power also was reduced 3%. So let's calculate it. We have the net power of 1,100 megawatts times 0.03 for this 3%, and we get 33 megawatts loss. And it happened for 12 weeks. And let's convert this to hours. 12 times 7 times 24. We get 2016 hours. So from this, if I can fit it, let's write it in the bottom. 2016 hours times 33 megawatts, we get 66,528 megawatt hour, to be precise. Okay, now that we have all our losses calculated, we can calculate the total energy loss, which we will use in our performance metrics calculations. So let's name this energy loss. This refers to the total energy loss that we have. And here, simply, I will plug in all the numbers that we have calculated before. So we have a planned loss here, unplanned loss here, and also 2 external losses here and here. So let's sum them up. So we get 802,032 megawatt hour total energy loss. Now we can start our performance metrics calculations. And why do we need these calculations? We need them because we want to see how our power plant actually performed during this one period of time. First metric we are going to calculate is energy generated. You can think of this metric as the total product delivered to the customers. So how much energy was actually generated at the end, considering all the losses. So naturally, energy generated, EG, is calculated as the reference energy generation, assuming the power plant worked the whole time continuously for 1 year, minus the energy losses, the total energy loss. So let's plug in the numbers. We have the reference energy generation of 9,636,000 minus 802,032. So these are in megawatt hours, equals 8,832,968 megawatt hour. And this is our energy generated. And this will be useful for the calculations of the next metrics that I'm going to show. So the second one is load factor, LF. And this tells us what plant actually provided in percentages. So you calculate it as the energy generated divided by the reference energy generation. So we can quickly calculate it here, plugging the numbers, or not to forget, times 100 to get the percentage. So our EG was 8 million. Let me plug these numbers quickly here. Divided by reference energy generation. Equals, again, we put the times 100 here. We get 91.68% load factor. Then we are going to calculate energy availability factor. And this tells us what the plant could have provided. What was the available energy? So energy availability factor. Also EAF. So how do we calculate this? Reference energy generation minus total energy loss divided by the reference energy generation times 100. Let's plug in the numbers. 91.68%. So if you noticed, our load factor and energy availability factor are identical. It means unless the plant has available but not used energy, they're going to be identical naturally. And in our case, there is no available but not used energy, so they are the same. Now we can calculate the unit capability factor, UCF. And this tells us how well the plant was maintained. What was the capability of the equipment in general? So how do we calculate it? Reference energy generation minus, then we have another parenthesis, planned energy losses plus the unplanned energy losses divided by reference energy generation times 100. If you noticed, we only have the planned and unplanned energy losses for this calculation, and we excluded the total energy loss because it also includes the losses of the external factors like the high temperature and the grid reducing the demand. This is about the unit capability, so our power plant units capability factor. That's why we don't include the external losses here. Let's plug in the numbers. 93.29%. All right. So lastly, you have the operation factor. And this is the percentage of time plant stayed online. Let's say the lights were on and we were operating. So operation factor. OF. How do we calculate this? This is basically the reference period time in hours minus, let's put the parentheses here, plant outages also, this is going to be in hours divided by our reference period time. Times 100. So let's plug in the numbers. 8,760 hours minus 504 hours for the planned outage that we already knew, and 8,750 hours gives us 94.25%. So that's all for the video. I hope now you know more about the nuclear power plant's maintenance and operations, and you will be able to perform these calculations by yourself. See you in the next video.